Okay. Right, here we go. Transequatorial propagation at VHF-UHF. So, how is it defined? Well, that multi-syllable word kind of tells you, but hides all the details. So it involves the reliable reception of signals or the making of two-way contacts over very long paths, that's thousands of kilometres, that cross the geomagnetic equator on frequencies well beyond the usual MUFs, and often at unexpectedly high signal strengths. But wait, there's more than one. Afternoon type is experienced predominantly between 1400 and 1900 local mean time, relative to the path midpoint. That's important. Evening type predominantly occurs between about 2000 and 2300 local mean time, again relative to the path midpoint. Each is now referred to by their modes. Way back when, in the post-World War II era, when amateur radio was reactivated around the world, a couple of curious things happened with the VHF allocations. In April 1947, XE1KE in Mexico City worked LU6DO down near Buenos Aires on 50 megs, an astounding distance of 7,000 kilometres. There was lots of rubbish, of course, about couldn't be done, skeptics, yada yada, conspiracy, all the rest of it. But it was reported in QST's World Above 50 Megs, run by Ed Tilton, W1HDQ, and it opened a Pandora's box for amateurs on VHF. The reports continued in those journals which carried a VHF-UHF column, which includes amateur radio in Australia. So, there's a glimpse of what we're talking about. Next, Ed Tilton reported again in 1947 that W7ACS in K86 in Hawaii worked VK5KL on 50 megs, a staggering 9,000 plus kilometres. There we are. There's a bit of a view of it. Again, there was a lot of scepticism about it, but then just to make sure, people still hammered away at it just to see if something could be in it. So in 1950, Tilton reported this phenomena to the scientific community at a meeting in Brussels. The title there is in the middle lines. They didn't notice, not until the 1950s. Meanwhile, 6 metres was open for business. Now became a citizen science phenomena. There was collaboration with the scientific community, 1950s through the 1970s, with amateurs and the various scientific establishments around the globe, including and perhaps especially in Australia. Scientists with amateur licenses drove ever more studies, like Villard, Stein and Yeh in California. Oswald Villard was a well-known amateur back over the 1950s and 1960s. Amateurs contributed to scientific projects. There was one in 1965 called Task Bridger between Australia and Japan. I actually took part in that, listening for the JA1 IGY beacon unsuccessfully, but that means something as well. The US Stanford University radar studies of the 1950s and 60s, backscatter radar over the equator, and IPS Australia in the 1970s, again in which I was involved. Afternoon type TEP. Propagation involved 2 F-layer reflections, each at around 20 degrees north-south geomagnetic latitude from the geomagnetic equator. Classic caudal hop. Looks like this. So you get the equatorial anomaly, which is created by actually a solar impact on the geomagnetic equator, or sorry, equatorial ionosphere, which drives electrons vertically upwards, and then they drift either side of the equator and drift down into the equatorial anomaly, and that builds over time as the world rotates. So the lumps either side are called anomaly crest, or the equatorial anomaly. That usually refers to both crests. So you can see the transmission paths illustrated there. When you look at the electron density either across the equator, this is the sort of diagram you get. That one was, in fact, a series of measurements in a 1970s project by IPS Radio and Space Services, whom I used to work for. The maximum observed frequencies of afternoon TEP typically 40 to 55 megs, sometimes up to 60 or 70 megs. Path lengths range typically from about 4,000 kilometres up to 10,000 plus kilometres. Often strong, steady signals with minimal Doppler shift. Peak seasonal occurrence is equinoctial. That's important. Occurrence rates follow the solar cycle, so there's more occurrence at solar cycle peak and less in the trough. Afternoon type TEP is also called supermode TEP, if you're looking through the literature. Here's a recording I made in Townsville of the JA2IGY beacon on 50 megs, 52 megs. Now you can see the Doppler shift is quite narrow, only a few hertz over a short period of time, but the signal strength is quite something. So rising to minus 60 dBm. So you're getting millivolts in the antenna, and that was just with just a 3-element 50 meg Yagi, horizontal of course. So at IPS they did a number of studies, and fortunately the number of ionosondes that were between southern Japan through across the Philippines, Papua New Guinea into Australia at around 150 degrees geographic longitude enabled the organisation to take measurements and provide a graphical arrangement so that they could make ray tracing of how the paths go. So this is a hand-drawn copy, a hand tracing actually, of a printout on the old fanfold paper, dot matrix on the old landfly paper, so that shows the focusing effects, which is, you can see it focusing on the right-hand side there, just above Townsville. This is of a real-time circuit. There's that measurement of the crests, of course, FOF2, or which of course is directly related to electron density across the equator. You can see the peaks at around plus or minus 20 degrees geomagnetic. So, our Pacific playground on 6 metres. It looks like this. Anybody who's been on 6 metres for a year or two and reads all of the now of course all the commentary online, You can see what I mean. There was an amateur in the Cook Islands whom I met, ZK1AA, who did a number of transequatorial studies recording signals from Hawaii right up to the 108 meg VHF FM band, and he published a number of studies, incorporated with some projects with IPS. So we come to evening type TEP. Propagation is via ducting or guiding through equatorial plasma bubbles, so it's totally different to afternoon type. These are field-aligned bubbles or fans of depleted ionisation threading the nighttime equatorial ionosphere. EPPs extend symmetrically north and south of the geomagnetic equator. That's important. Path lengths of 3,000 to 6,000 kilometres, occasionally up to 7,000 to 8,000 kilometres. Indeed, the Australian record is VK4BFO out Mount Isa to Hokkaido in northern Japan, and that's just over 8,000 kilometres. I think that's one of the, there's only one, I think, other path that's greater than, that was achieved greater than that, is in Africa. That was, but 4BFO was on 2 metres, of course, that was on 2 metres as well. So the maximum observed frequencies often extend to 144 megs, rarely on 432 megs. There are perhaps 2 known contacts and 2 or 3 known beacons heard. It's also known as ducted mode TEP for obvious reasons. So predominant occurrence is between 2,000 to 2,300 LMT, and it sometimes extends. Might start earlier, occasionally extends past 2,400. Openings can last 20 to 30 minutes, and they rack up one after the other. So, sometimes less than that. A series of openings often occurs up to 30 minutes or so apart, or semi-continuous, overlapping. At the higher frequencies, durations of openings decreases. When the sun sets on the equatorial ionosphere, the base rises in altitude at about the time 1900 to 2000 LMT, just as afternoon type begins to fade out. The more viscous F layer flows over the less viscous neutral ionosphere. This sets up what's known as a Rayleigh-Taylor instability. It's sort of like oil on water. Ripples form in the base of the F layer. The middle of a ripple, having little ionisation, rises into the F layer, forming a bubble that swiftly elongates along the geomagnetic field lines. That swiftly means minutes. Consider the size of that. It flips into that bubble right through to the middle of the F layer very, very swiftly. So here's a look at bubble development. On the left, there's the start. Takes about 10 minutes to look like that. And at 14 minutes, it's almost doubled in height. 17 minutes, it's tripled in height. And of course, it began to bifurcate very quickly. So it splits into a number of parallel bubbles. Here's a cross-sectional view from a VHF radar mounted in Indonesia, very close to the geomagnetic equator. So you see those bubbles are quite large and quite widely distributed in a east-west direction. So here's the mechanics. You get bubbles that begin and then they rise to quite heights, high heights, yes. Peak up peaking up to about 1,500 kilometres. The bubbles can be 1,000 to 3,000 kilometres long. Propagation into them is at elevations between about 2 and 20 degrees. You can see bubbles from Darwin in a radio sense, and you can also do it with a visual sense with aeronomy video detectors or light detectors. I don't have any pictures. I do, but I don't have them in the presentation. So here we are. The bubbles rise at speeds of typically 125 to 350 metres per second. They drift eastwards at speeds of 25 to 125 metres per second, and that's due to winds in the earth layer. Some bubbles have been recorded rising at greater than 2 kilometres per second. They reach heights of 1,500 plus kilometres at the geomagnetic equator, as I said earlier, and the feet can extend to greater than 25 degrees geomagnetic latitude, which probably was the case with VK4 BFO's magnificent contact. They can be 40 to 350 kilometres in diameter, spaced around 40 to 100 kilometres apart, and they may be bifurcated, that is, think like an elephant's trunk, as you saw in the illustrations earlier. So here's some mechanics. Here's the sort of diurnal characteristics of JA-VK contacts. The dashed line shows the development of, or the recording of EPBs, and the histograms show contacts at 2 different frequencies. You see the peaks in occurrence there before 2100 local or around 2100 local mean time. Here's what a recording looks like of a series of beacons put up by the Defence Science Technology Organisation in Darwin, running 500 to 750 watts to 7-element Yagis, aimed at Japan. The recording was made in Yamagawa in a special radio and ionospheric facility there, which is still going. As you can see, the top is at 48.45 megahertz. The second one is at 72 megs, and then, 72, and then the top one, the bottom one I should say, is 102 megs. Yeah, can't read it. So here's the seasonal characteristics. It's very obviously equinoctial. So this is 48, 88 and 102 megs beacon recordings mapped out, and 144 megs between Darwin and Japan. It's quite salutary exactly what's going on there. So, in inverted commas, the best paths are bisected by the geomagnetic equator, and across the geomagnetic equator with a small range of angles close to 90 degrees. Path terminals commonly lie in a zone between about 10 degrees and 30 degrees geomagnetic latitude, that is, nearly magnetic conjugate. Paths having an obliquity of 15 degrees or more to the orthogonal experience far fewer openings. Point north, brother. The higher the frequency, the closer to orthogonal it needs to be. Here's our region, evening TEP playground, with the 10 degrees and 30 degrees geometric latitude mapped out. And here's the path generally worked on 6 and 2 metres via TEP. Note how the path terminals are near the conjugate areas. And curiously, off-path signals have been recorded. For example, between Singapore and JA. I once saw a presentation by a DSTO scientist who took a trip to Singapore to see if his theory about the guides, the bubble guides being leaky. So he took a receiver and a handheld antenna, went to the roof of his hotel and recorded, I think, the 72 meg signal pointing straight up, which is, you know, when you think about it, yeah. So, here, more mechanics of the bubble. So, if you're going to work evening type TEP, you've got to think of the mechanics of entering and exiting a bubble. The ray path tangent to a third line at the height of entering a bubble. If you look at the diagram, of course, you can see an idealised version of a plasma bubble. And to enter it, you have to be in that acceptance cone, which forms a sort of an ellipse on the ground. Elevation angles ranging from 2 to 20 degrees. As I said earlier, there's the cone of acceptance and that communication zone on the ground. The radius of this zone is given by equals 1.42 times 10 to the 14th divided by the frequency of operation. So for 144 megs, it's about 987 kilometres in diameter. At 432, it's 329. It's still a fair range, but...
It's a conical horn at 50 megahertz.
Yes. So, anyway, we'll come to that on higher frequencies later. So, here's our situation for the best paths. The dashed ellipse in the top diagram is those areas most often worked from Darwin. Reported 2 metre contacts from VK4, JA cover all those call areas 0, 1, 2, 3, 4 and, sorry, 1, 2, 3, yeah, 4 and 7.
And then it's like local contact. When you're in Darwin, it's like a local contact.
Yeah. Darwin Ammon's got jack of it and bored with it and stopped making contacts. They should be ashamed of themselves. And you notice, of course, it's close to conjugacy. And the paths cross the geomagnetic equator at or near 90 degrees. What am I doing? Now, on a global basis, here's the South American situation. So, if you look down there at the CX and LU, etc., they're working PJ4, KP4, Puerto Rico, etc., Venezuela. And so that sort of holds up the general mechanics. And the South Americans have been hammering this particularly over the last few years. They forgot about it for a while, and around 2020 they jumped on it again. There have been contacts on 70 centimetres across the gap there. So, but only a few. Again, so many sort of go, oh, this is fun, you know, get on 2 metres. And, you know, you ask them to go to 1296, sorry, to 432. And of course, like No, I'm having too much fun. Same thing with the African-European section, getting into the Middle East from East Africa and from Southeast Africa into Greece, the Middle Mediterranean, and of course, well, Namibia, am I right? Yeah, into Southern Europe. So, here's the next challenge. Extend the MUF boundary. We've only got a few instances for 70 centimetres. It may be possible to use 1296 megs. Scientists are very interested in equatorial plasma bubbles. I've logged more than 1,500 scientific papers on the subject since the 1970s. More than half of those over the last dozen years. It is a huge thing. And there's a reason for that, apart from just wanting to know the physics of it. It's because those bubbles interfere with satellite, particularly geostationary satellites, and they do in fact knock out communication circuits. And those they're talking there at 1.5 gigs. So if the propagation is kind of like a continuous scatter mode. So if it can knock out 1.5 gigs, it might support 1.5 gigs. Nobody's tried it, not even the scientific establishment. So how do we go about that? Well, to push the MUF boundary, you've got to plan around the path loss. It's kind of like moonbounce. This table of excess path loss was compiled by SV1AB and I can't remember the other gentleman, ZS. But for our region, what you need to do is, well, first of all, sorry, going back to the excess path loss, if you add 1296 megs below in the lower imaginary line row, the excess path loss is another 15 dB down, roughly, which puts it in the domain of digital modes. Now, there's a lot of people having a lot of fun with 2 meters on FT8. The South Americans don't often use voice much more. Well, for a start, you know, at one end they speak Spanish, at the other they speak Portuguese. There's kind of a language barrier, not to mention English and the other two. So there's a lot of fun being had on FT8 in South America. But it would be important, given the narrowing of the specifications in the path, to arrange skits. Choose times around when the sun sets simultaneously, not saying that well, simultaneously on both path terminals. So, which of course puts it at the equinoxes. And you need to find a way to know when the bubbles appear. There are no ionosons in the right spot anymore that serve us. The nearest one is at Trivandrum in the southern India. And it's not always online and it's not real time. You can tell when it's there from, if you're running 6 meters, So once it starts on 6 metres, you can step your way through, because you can hear the signal characteristics, and that gives you something now. What some people used to do in the past, and what the scientific community did, was use, well, in Japan they used Radio Australia on 21 megs as a means of determining if there were bubbles present. So I've got some of my concise papers on the subject online. Use the tiny URLs best. And my supervisor at IPS back in the 1970s, Dr. Leo McNamara, published his last scientific paper just 2 years ago, and became a silent key. But that evening type TEP on Japan-Australia circuits by McNamara in 1972 is one of the classic papers, is often cited. Okay, questions? No questions.
I know there was a group of amateurs, of Australian amateurs, who wanted to investigate going up to the Northern Territory and trying deliberately to work 2 metres into Japan.
They did it all the time.
They were doing it all the time. They wanted to see how far they could stretch it, and they had a very simple technique. They got a big map of the Pacific,
yeah,
and they worked out, well, there's the equator, here's the geomagnetic equator, which is not the same thing, and they folded the map along that line.
Of course.
So they folded it straight in half, just like that. And they said, okay, all the amateurs are in Tokyo, so they got a pin and they pushed it through Tokyo, and they saw where in the Northern Territory it popped out, and that's where they went.
Very smart.
So that they were exactly at 90 degrees to the geomagnetic equator, and the same distance out, which is where the best path loss is. And they said, well, we'll leave the amateurs alone in Tokyo, and that's where we'll go. And they were quite successful doing that.
Stricken sealing wax science.
Stricken, exactly. There's a lot to it in there. I didn't realise you could go as high in frequency as that. I must say, I thought 144 was the top of the tree, but clearly that's not the case. And certainly it's not going to be the case with high power big aerials and digital.
Exactly.
There's a lot of work to be done up there.
Well, 6 metres has been coming alive in the afternoon, then disappearing and coming back again later at night at about 11 o'clock at night.
There it is. Every day in the last month, it's the afternoon TEP into Tokyo and Japan.
And big signals too.
Huge signals.
Yeah, well, they tend to run more power these days up there as well.
Yeah, well, only just run the barefoot 9300, 7300, sorry.
Well, the Japanese were only allowed to started to use digital about 4 or 5 years ago, when we started working them on JT65, which was the best we had at the time, and that's 2 minutes per contact, and they were so keen to work us at that time. You just you could keep filling the logbook up until you were bored sick of it. But they were really keen to work us. But with some of the really flash modes now, Q65 FT4, with a 7-second turnaround time, it's real speed dating. You can't even write it down quick enough.
Yeah, you caught me the other day.
So there's a lot to be done.
You're talking about like FT4 and FT8. With huge signals, they're S9 plus. So I dropped down to 110, 120, 130 and put out some SSB calls. Not a skerrick. I might have had 2 or 3 SSB contacts, but you go back down to the FT8, and it's just waterfall, just full.
They
do. You think, oh, I'll just duck up and we'll go for a CW contact. No.
Well, they're having so much fun on FT8.
Yeah.
So, Roger, the contacts that you Brisbane to Mexico and North America in 6 metres, that's not TEP?
Yeah.
to Mexico. That's actually the
Oh, yes, it is. Oh, let me go back there.
It's a great single half direct crossing.
that's a couple of hops.
Yeah. So you see the dashed lines. That's where the equatorial anomaly is. You can actually see that, or see the top part of it, from Brisbane at about 2 to 3,000 kilometres away.
So 3 weeks ago, I thought we were screening up for the US operators on the west coast, 6 metres. One afternoon, it was amazing. And Mexico, and sort of very between Mexico and California. Yeah. Like that.
Early morning? Okay. During the last season, most of the contacts that I've been involved with from here to South America and up into the Caribbean were all early morning stuff, and it was all going over the pole. So it's double F2. Well, yes, that's what we assumed. That's where you had to point to get them.
Sorry, probably wrong.
Oh,
okay. It'll be. So what was the time here?
Sort of 6, 7 o'clock in the morning.
Yeah. And where is the midday mark on the world?
That's a very good question, Roger. Where is it?
Yeah. The straight up and down line in the middle there.
Okay.
And so they've got, it's afternoon, and you've got the morning. So if you want to work those paths on afternoon type, what you do is you look at the time, you look at the midday between you, and so that you sort of then subtract how many hours you are away from that point, and how many hours they're away from it as well.
Okay. Against that, all I know is that you're having to aim at 160 degrees, over the top of New Zealand, which would take your path down transpolar to get into South America.
Was that the way you get into the bubble then?
Well, you're aiming over New Zealand.
Or south of New Zealand, yeah.
So if you fly northeast, you get nothing, or you didn't try.
No, we did. We would point it.
I think
you might be getting it off the side of the beam.
Okay. I didn't think so, but I can't be sure. All things are possible.
I have a question for you. Sorry, I can't get the video to work, but anyway, you just have to talk to a blank face. But there was one thing that I did notice, and I was just wondering, first of all, is there any telltale noises that sort of gives you a hint of this type of happening? Like any sort of anything at all, or is it just going to be a signal that you pick up?
If you can hear the noise floor, and most modern transceivers will be able to do that, and even with on 6 metres with a 4-element or 5-element Yagi, if you can hear the noise floor, you will hear the noise floor rise, because you'll be picking up noise from across the equator. You'll also be picking up, basically the collection of thunderstorms noise, which makes the noise floor rise.
Roger, would you hear
the second thing,
like on a barbecue or anything like?
No.
What sort of noise? I think that's what John's actually alluding to. Is there a specific noise that you'll hear?
Nothing specific. I've hung around on 6 metres and heard it. You can hear the noise floor rise. And then you tune around and find some signals.
The reason why I asked the question was I've been doing a lot of 1296 work of first up in the morning. Now, in some cases, and nobody's actually told me any more than whatever hearing this, there's been this funny, that radar that you get on HF, I forget, over the horizon radar.
Yep.
That particular noise, not necessarily is it that, but on 1296 every now and then there's this weird noise that comes through what I call the band of 1296, and I'm not really moving that far on it, but I thought maybe it might have been something like you're suggesting, or it may be something completely different. But there was someone mentioned that you could hear it better at the airport than you could at other places. But I can't describe it. It was just a weirdo noise, but not necessarily like that. That radar over the horizon radar this noise, but something like that. And I was just wondering whether that was something that could have been attributed to what you were talking about, or not.
Unlikely.
Unlikely. Okay.
Roger, could I just ask about the speed of movement of these things in relation to the speed of rotation of the Earth underneath it all?
Yeah.
Is it dragging the chain, or is it going faster than the speed of the Earth?
Well, the equatorial plasma bubbles, rise at 100 to 300 meters per second, but they drift to the east.
Right.
So they're
going faster.
But it's sort of like vehicle speeds.
Mm-hmm.
So they take about 20 to 30 minutes to drift out of view, and then another one comes along behind.
So how about then LU and that sort of prefix? That's not TDP then, because it's sort of going across the equator.
No.
Just a minute, let me get down to that. Well, maybe I should go back.
So what the header LUs as well, and that's sort of odd times of the day.
Right, there was that one. So, your question is?
From the east coast of Australia to LU, 6 metres.
Oh, if you working LU from here, that's sporadic E.
That's definitely, yeah.
I've researched those paths and the transpolar paths as well.
Remember you're doing that multi-quarter talk.
Yeah. Yeah. So, any further questions?
Intriguing.
Have I stumped everybody?
I was just going to comment, we were talking about it in the car on the way over here. The contact between Hokkaido in northern Japan and Mount Isa was direct sort of, remember we talked about it, folded the map over on the geomagnetic equator. That was very typically, if you folded it over, Hokkaido, the northern part of Hokkaido, would be very close to Mount Isa. But those other blokes that were up in Northern Territory were only focused really on Western Japan. Japan sort of comes around.
Yes. Because Japan sort of like, shall we say, rises to the northeast. Mm-hmm. And so it gets off that orthogonal path. It's more difficult to work it from Darwin than it is from Queensland.
Oh, I can see a road trip coming on.
Yeah.
Just do some read-ups on VK4's ZSH.
Well, that was Alan Downey and them, wasn't it?
Alan Downey. Yeah.
They did it in a Ford Zephyr.
Certainly a souped-up Ford anyway.
Yeah. Yeah, he's given up. I'm pretty sure I've got his copy of his logbook from that.
Oh, he's still there.
Okay.
He's still there in Sheldon.
Hmm. Well, thank you, Roger. That was a very inspiring presentation. And it's actually asked a lot more questions than it's answered, in fact, but
that's the object. I love doing that.
That's really good.
When you do make that contact, how do you know it's sporadic E or T? It's just the time of the day and the characteristics of the signal, and how would you categorise it?
What, crossing the equator on sporadic E?
Yeah.
It's much more difficult than you think. That's a really odd one. You can tell by the time of day. For a start, To cross the equator on sporadic E, you would have to do it daytime because of you would need to use
The entire path has to be in daylight.
sporadic E sort of in the equatorial, which forms every day over the geomagnetic equator. But it dies once the sun sets, or actually before the sun sets.
The entire path has to have daylight.
But yes, so that you get sporadic E in the daytime, but the critical one is hopping across the equator. You need that reflection from magnetic equatorial sporadic E, which is a daily phenomenon.
We need a kilowatt and some big yardies on 2 metres to go out to Mount Isa.
And a trailer.
And a trailer.
All you need is 100
generator.
watts. You don't need a kilowatt.
Generator or something. Yes. But is it VK8AW? Is that him up there?
Yeah.
He's constantly working. He was working them again recently on 144.320.
Yeah. I keep receiving files of his logs from somebody else, and I'm thinking, oh, this is.
Just doesn't work. And I think they've been doing it into Western Australia, or have they been the JA's been hearing the beacon from Western Australia?
Yes, so the beacons have been reported, and there are certainly been reports from up in the northwest coast of West Australia, but not on 2 metres.
No.
No, 6 metres, yes.
No,
2 metres,
6
no.
metres is pretty easy to do.
Well, the other thing is, of course, that the whole thing also includes, the geometry would include Korea, of course, South Korea, and of course China. China's been worked on 6 metres via evening TEP.
They were in again, not last night, not before, on 6. Oh, that was Monday night.
Yeah, it's good.
Yeah, I worked a few Chinese. 6.
Well done.
Well, they're in there with the JAs all the time.
Yeah.
Mixed in, you see Republic of South Korea, China and Japan, JAs all come in at the same time.
It's funny watching the 10 metres that all come together.
Yeah.
All
6 is the same, like they just roll in. And if you really want to upset yourself, just put one call out. Yeah.
I did that once on 10 metres, FT8 went up to the hell of a shit, and the whole screen was like red.
Yeah.
These people said, "Hey."
I was doing it on FT4 for a chuckle and somebody local answered. But they must be monitoring, because like you'll be FT8 just full and you think, oh, FT4, put a couple of calls out. They must be monitoring, because next year all of a sudden you're getting hammered.
Yeah, you hit one of their clusters, and the first one that sees you spots you on the cluster, and then all of a sudden you're.
You can spend 15 minutes there and roll 20 contacts. Just clear the airflow, clear the airflow, clear the. That's right.
Back in the old days, you used to have patience.
Yeah, FT8's going to kill the hobby.
5 contacts was a good day.
Mm.
Oh, well, thank you, Roger.
Yeah.
Perhaps we could all thank Roger properly in the traditional way.
Oh. Yeah.
Thank you very much.
All right, perhaps we could unshare now, and we'll see if any of the guys on the screen have got anything they want to say. Anything from the team's team?
Hang on, he's got himself a VK5 call sign now. What are you doing?
I do.
Yeah. Yeah, just one quick question for Roger.
Yeah.
I worked through to Kuwait about 8 o'clock one night in April last year. So what mode of contact would that be?
What would be the time in Kuwait? Probably early afternoon. What month was it?
April.
Oh, it's probably sporadic E.
Oh, okay.
But it might be sporadic E and TEP.
Okay. Yeah, very brief opening.
Yeah, it's probably a joint thing, sporadic E and TEP.
Yep.
Oh, speaking of which, Brian VK5BC has worked Sicily, yeah, Gibble Manor in Sicily, of a late afternoon, on exactly the same day, 11 years apart.
Wow.
Oh, wow. Someplace like that.
Interesting.
Roger, I have a question. How do we detect those plasma bubbles? What sort of equipment are you using?
Radars. There was a 50 meg radar, and I mean exactly 50 megs, because they were measuring, using it to measure characteristics in the ionosphere of a given size. So, they break up the characteristics in the ionosphere into, those 1 metre and below, those 3 metres and below, etc. Things like that. So there was this, at a place called Jicamarca in Peru, which is northeast of Lima, there's a big scientific observatory site there. So they had an antenna made of coaxial dipoles with 128 elements. And they were running, firstly, 100 kilowatts and subsequently a megawatt. Straight up. And of course, the near field is then at 100 kilometres. And you get reflections. But they used to run programs, throughout the day, and they can measure the specific density of specific ions with it. In that, well, they can measure the electron density, full stop, to very close margins. So they would run these things at night, and these weird diagrams would appear. Big smears, instead of just a nice line reflection, there's these huge balloons would appear. And of course, everybody's scratching their head, what the hell is that? There's a famous paper by two guys called Woodman and LaHoz. Woodman is from the US and LaHoz is a local guy, which set it all out. And they suddenly realised. Actually, I was at a meeting when everybody realised that they were plasma bubbles. So that it took some years. It took the best part of 10 years for people to realise there's a connection between spreading on the ionograms that you get, called spread F, and these plumes you used to see on the 50 meg radar, and it is plasma bubbles.
Big one.
And how long do they get end to end?
Sorry, say again?
How long do they get from one end to the other?
It was in the diagrams.
So actually, perhaps I know the answer, but I think you talked about plus or minus 20 degrees.
No, that's the entry angle.
Well, they're firing straight up, and they're getting reflections from the small changes in electron density that you get. Well, actually, it's a large change if there's a plasma bubble, because it's empty on the inside, and the edges are compressed somewhat ions and electrons.
You want to know how long the bubble is?
Yeah, no, actually, I think we.
Oh, right, how long the bubble is?
10,000
Oh,
kilometres.
yeah, no, they're typically 3,000 to maybe 5,000 kilometres long. If they float real high, it gets even longer.
It's the same principle that Kevin and Scott worked the 3.4 gig contact from Mount Mobile and to New Zealand that time. That was because I think Rex 7MO used that data and all the weather and everything to actually plan his 10 gig contact across to New Zealand also. It was a similar, I'm led to believe.
Similar principle?
Similar principle.
Probably.
It was a duct.
Yeah, it was Tropo that day.
Except one's in the atmosphere, the other one's in the ionosphere.
Yeah. But I remember Gibbs Tech, somebody gave a talk on ducts and they talked about the inside of it being like an elephant's trunk. And that's where you get the noise from inside. Is that correct?
That would have been Andrew Martin.
Yeah.
And you might be right.
Yeah, that's. I just remember it was interesting that they talked about, you had the proper word for it, but he said it was like an elephant's trunk.
Yeah, bifurcated. Yeah,
Bifurcated,
it's split.
yeah.
Yeah, that's right.
I prefer you to be talking about boobies, that was fun.
Yeah. But yeah, but getting back to that, like
Cool.
John was asking for, like noises and stuff that you can hear. Like the signals vary and change, and that's what you listen for. That's the whole idea of beacons, is to flip off and have a listen for.
Yep.
Well, listening for noises, there were some very clear noises off the sun in the last 3 or 4 weeks as well. There was a solar flare, and the noise on 6 meters, as I was sitting there listening to it, just came up enough to really, what's she switched on in the kitchen now? and the noise is roaring through. If you listen, there's lots of stuff out there.
But trying to identify what it actually is,
Yeah.
is the hardest part.
Yeah. But Pete's point's very valid. You know, when you do make a contact, how do you know what mode of propagation are you actually using? And because you're beaming at 160 degrees, is that actually, unless you physically go around and check, how do you know that that is actually the path that you're looking at? It may not be.
Can you
You
spin your
assume it
antenna
is.
fast enough?
No, you can't.
No.
That's the problem. By the time you've gone in, things may have changed.
Quite frankly, I don't care. I just don't, I've got the contact.
Just work it.
Yeah, just put it in the log.
Just work it.
When I
Yeah.
went to the west coast of America on 6 meters, I was pretty damn happy. For me, that was a big achievement. On 3 of an RPA, it was.
Barefoot.
No, I was using my Mr. SPU, so 399.95 watts.
139 point.
Oh, 119.95.
Yeah, that's it.
Okay. Well, thanks everybody for joining in tonight. To Roger for
Yeah, thank you,
presenting
Roger. That
to
was
us.
great.
Yeah,
Thanks to
okay,
all you guys
pleasure.
who come in from on Teams. That's made it interesting.